we have a ball on a, say, a very smooth table. And this ball at first, all right, let's suppose that this ball has a certain velocity. I'll call that, let it be u. Right? It can be maybe 1 or 2 or 3 meters per second or whatever. And after some time, after say a time t, the ball travels to here. Okay, and let's say it's accelerating. So when it reaches here, it has a bigger speed. Let's say the new velocity is v. Okay, and in between, suppose that the displacement from there to there. Okay, so suppose that the displacement from there to there is given by s. So s is the displacement. Okay, now I need so along the way, as it's accelerating, let's say that the acceleration, all right, let's say the acceleration is given by a. All right, I'll let letter A be the acceleration. Now what I'm going to do is to derive formulae that relate all of these quantities, u, a, b, t, s. I shall start with the simplest, which is just the definition of a. The acceleration. Now we have already seen the definition of a. The acceleration, is equal to the change in velocity, in this case the final velocity minus the initial velocity, okay, divided by the time taken. So that gives us that's the definition. Let me write this down. Definition. Now, definition means, in simple words, it means can be an equation or a symbol or a word that is just, if you like, kind of made up. All right, so that it's being made up because it turns out to be useful. There is no reason behind it. Okay, that's the first and simple way to think about it. But usually there's a reason behind it, and the reason behind it is simply that it works. Because it's useful. That's why we want to use it. Okay, but there's no reason behind it in the sense that it is not something that you can derive from something simpler. Okay, or not, at least not in any obvious or basic way. But okay, so this is just a definition. Let's think about it. Acceleration as change in velocity over time. So from here we'll derive our first equation, which is really just a rearrangement of this. So I'm going to multiply both sides of this equation by t. Right. I'm going to say I'm going to multiply both sides by t, so that on the left side I'll have at, and on the right side, when I multiply by t, the t here at the bottom gets cancelled off, and I have v minus u. Or we can think of it as just bringing the t over to the other side. Alright, and now I'm going to rearrange this by adding u to both sides. So on the right side, when I add u, it will cancel off with the minus u, and I'm just left with v. And on the left side, I will have a u plus a t, right? Or I can just think of bringing the u over to the other side. So I'm just going to write this down a bit more neatly. So v is equal to u plus a t. So I've just derived my equation number 1, my first equation. So this is nothing more than a rearrangement of the definition of acceleration. Okay. So now I'm going to derive my next equation. Okay. Now to derive my next equation, I need to draw a graph. What I want to do is, let's see. Okay, I'm going to draw a speed time graph here. The speed time graph, velocity time graph actually. I'm going to start by drawing a velocity time graph. So, right, that's time. And now for the velocity, this is the velocity axis. I'm going to say, right, suppose that the starting velocity u and v, right, suppose that those two values are somewhere here and here. Okay, so that in the beginning, when the time t is 0, the initial velocity is u, so it's there. Now after a certain time t, let's say there, let's say that mark there is given by the time t. The velocity then is given by v. Okay, is given by that value there. So therefore, the graph would look like this. Just going to join the 2 points. Okay. Now this straight line here, what this straight line here means is that we are assuming we are taking this acceleration to be uniform. So this is an idea that I need to write down clearly. We are going to assume meaning that we are just going to take this as an example, just take this to be true. We're going to assume that the acceleration is uniform. Now what does acceleration uniform mean? Actually, it means that the velocity time graph is a straight line. But why is that the case? Right, acceleration, if you remember, is the rate of change. Okay, it's the rate of change of velocity. Okay, it's the change of velocity divided by time, which we've written down just now. So it means that every second, if we say that acceleration is uniform, it means that every second the velocity increases by the same amount. Alright, so that's why when you plot the graph, you get a straight line, or velocity against time, you get a straight line, because every second it goes up by the same amount. That's the simple reason. Okay, so what I want to do now, what do I want to do? I want to find a formula for the displacement. Okay. I'm going to find a formula for the displacement. How can I do that? Now we have already seen that displacement is the area under the velocity time graph. So let's check that out. That's the velocity time graph, and the area under it. The area under the velocity time graph is given by this. Let me just shade this area. Is this shape here? Now, what shape is this? How can we find this area? Well, you notice that this shape here has two parallel sides. But the other two sides, this one and this one, those are not parallel. So what we have here is a trapezium. And we know how to find the area of a trapezium. Area of a trapezium is given by, let's see, I'll write this now. Half, okay, of the sum of the parallel sides, meaning half of this side and this side added together. So let me add those two sides together. Let me write this down first. Is half of the sum of parallel sides. Okay. Times the next part of it. Times what? Okay. Times the distance between them, actually. Times the distance between them. Distance between. So that's actually the formula for trapezium, which is the name of this shape. Alright, let me write down the name of this shape as well. So this shape here has a name, and that name is a trapezium. So trapezium, T-R-A-P-E-Z-I-U-M, the trapezium. Okay. So here we are, and with this formula, we can now find the displacement as in terms of the other quantities, in terms of the velocities and so on. Okay, so S is equal to half times sum of the parallel sides. Right, the parallel sides are actually U and V. Alright, the length of this side is U, and the length of that side is V. Okay, so it's actually U plus V, and the length between the parallel sides would be T. All right, T is the time from one the start to there. Okay. So that is the distance between them is T. And there we have our next formula. Alright, this is our formula number 2. We are now ready to take on the next two formula. Okay, let's try that. So we have this ball. Okay, we have the distance in between, and let's see, we have the starting velocity of U. We have a final velocity of V. Okay, and with the time in between of T, and when we have acceleration, okay, go faster and faster, acceleration A, and distance in between is S. The equation that we have obtained two equations. Now I'm going to work out another equation for the displacement actually. let's see how we can get this. Now, once again, we can actually get this from the velocity time graph. Okay, let's see how this happens. Now, the velocity time graph, you can sketch that again easily. Starting time u, final time v, and uniform acceleration. We are assuming uniform acceleration, so it's a constant gradient. Okay, every second velocity increases by the same amount. So constant gradient. Now, once again, I want to think about finding the displacement, which we already know is the area in between. And just now, I have used the formula for a trapezium. Now, this time I'm going to do something different. I'm going to cut this area. I'm going to cut this into two parts, so that each part is simpler than the whole figure. And you can already see that we have a rectangle at the bottom and a triangle on top. So what I want to do now is to find the areas separately and then add them up. Okay, now I know that displacement, what I want to find is a displacement. I know that displacement is the area, right? Is the area under the graph. Right, it's the area under the graph. Okay, so I'm now trying to find that by finding the rectangle area and the triangle area. So what's the area of the rectangle? Let's see, rectangle plus triangle. Now the area of the rectangle, okay, the horizontal side, this side here is t, and that side there is u. Okay, so it's just ut plus the triangle Alright, the triangle now is half base times height. So the height, right, the height now half is half times the base is t, right? T times, now what is the height? The height is here. This is the height that we're talking about. Okay, it's actually v, the difference between v and u. Okay, it's actually v minus u. Now, if we simplify this directly, we'll actually get back the previous equation for the displacement. But I don't want to get back the same equation. I want the answer in terms of the acceleration. So what I'm going to do is I'm going to make use of the definition for acceleration. Let me recall the definition for acceleration. Acceleration write this down. Acceleration is equal to the change in velocity v minus u over the time taken. Now if I can rearrange this to get an expression for v minus u, or the v minus u, which happens here? Simply by moving the t over to the other side. Alright, to the other side here. So that, in other words, the v minus u here is actually a times t. Alright, it's actually the a here times the t here will give me the v minus u. So therefore, I now have my answer. This is equal to ut plus half times t times at. So that's half a and then t squared, because I have a t there and a t there. So this is the displacement s. Okay, and this is the formula, the third formula that I've just found. And now we need one more formula. To get that one more formula, this is what I'll do. We can actually get that one more formula by combining all the formulas that we have obtained so far, which I'll start by writing down. So the first formula comes from the definition of acceleration. It is v is equal to u, right? The final velocity is equal to the initial velocity plus acceleration times time. The next equation relates displacement to the sum of the velocities, u plus v, divided by 2 times time. So this is the next one. And the third one is displacement is equal to initial velocity times time plus half times acceleration times time squared. And we need one more equation. Let's see how we can find that. Now the one more equation, we can find it in this way. We can find it from the first two actually. Let me first start by rearranging the first equation. I'm going to rearrange it to get, to get v minus u is equal to at. Alright, what I've just done is I've just subtract u from both sides, or move u over to the left. Now next, I'm going to rearrange this one. I'm going to rearrange this one. The idea is that I want to find v plus u. I want an expression for v plus u. Now v plus u is this. So basically I want to rearrange this so that I have just v plus u on one side. So I would, alright, I'll multiply both sides by 2, which is the same as moving 2 over to the other side. And I'll divide both sides by t, which is the same as moving t to the bottom of the other side. So this just means that v plus u will become 2s divided by t. 2s over t. Okay, so that's the rearrangement. And from here, I'm now going to derive the third equation, fourth equation, by multiplying these two equations. Now first, I'll multiply this by this. Now when I do that, I can expand the two. Okay, I'll end up with v squared minus u squared on one side, and on the other side the t and the t cancels, and I'll end up with just 2s times A. So 2AS. So that's my third equation. Now this equation is often written in this form, with V squared as the subject. So V squared is equal to, now I'll add U squared to both sides of this equation, or I can just say that I'll move U squared to the right. So this gives U squared, V squared is equal to U squared plus 2AS. And now I have 4 equations, right? 4 acceleration equations that will be useful. Now, but what's the point of getting all these 4 equations with so much mathematics? Well, if you look at the equation, look at each equation, you'll find that each equation contains a different combination of symbols. Here we have VUAT, okay, VUAT. Here we have SUVT, and here we have SUAT, and here we have VUAS. So the 4 equations contain different combinations of quantities, and this allows us to calculate the quantities in different ways. So for example, in the first one, if we know what is U, V, and A, we can find T. Okay, fair enough. But what if we want to find S? Okay, if we have U, V, and A, can we find S? Right, then you search through the four equations. You want to find equation as V, U, A, and S. Is there such a one? V, U, A, and S. There we are. So you would use this one. Just an example. And you can imagine other situations where you have different information and you can just pick one equation and use it. Hopefully.